So we need a way to analyze more complicated circuits. And we do that with these rules. If we want to Americanize the name or Texanize the name, in my case, it would be Kirchhoff's rules. If we want to go for the more legitimate pronunciation, which Professor Lewin does, so I think we should, it is Kirchhoff's rules. It's kind of fun to say, Kirchhoff. So it is a systematic way to analyze circuits. So there are two. The first Kirchhoff rule is the junction rule. And the junction rule, if we state it mathematically, it's simply the sum at a junction of the current equals 0. Or you could also just say current in equals current out. We know that charge has to be conserved, so we can't have more current going into a junction than coming out. So let's look at a circuit and a junction. So we could get a slightly complicated circuit going like this, have a battery, and have the wire come out and go, say, to R1 here, and then have it split off and have a second resistor and have R2 like that. When you use Kirchhoff's rules, you have to start thinking about all the currents that are going to flow through the circuit. And first, you just pick a direction. Well, in this case, it's pretty clear. If this is the positive side of the battery, that's the negative side. The current's probably going to go this way. So we'll say some current flows out of here like that. So we'll call the branch or the current going in this part I1, current 1. Then it's going to split. And then you just give it another name. So here, we'll say this is I2 going on the outside. This is I3 going down there. And then they're going to come back together, and again, this will be I1. And you can see it's all essentially the same wire. There's no branches in between. That's all I1. This line is I3, and this branch is I2. So let's look at this little junction right here. That's one of our junctions. So at the junction, we can draw it, zoom in on it. We have I1, I2, and I3. And you write your sum, you just say, here, let's sum them up. And when a current is going into the junction, it's positive. So you'd say, okay, the only one going in is I1. So I1 goes in, and the other two go out. So when one goes out of a junction, it's negative. So minus I2, and then 3 is exiting the junction, minus I3 is 0. Or if we wanted to solve it for I1, we would just simply say the other statement that I gave, I1 equals I2 plus I3. That is that you can't lose current. Okay? So this is a very simple way to apply Kirchhoff's junction rule in this case. We can even look at this other junction. Let's look at that junction and apply the same thing. Here we would have, let's see, I3 is going in, I3, and I2 is going in plus I2, and I1 is coming out, minus I1. Those equal 0. Then if you solve this for I1, you get the same thing. And in this simple circuit, you're not surprised. But this actually illustrates something, and that is that you can't apply Kirchhoff's rules just to everything. You will overdetermine your system. What we're trying to do is set up a bunch of equations and a bunch of unknowns to get an answer. And sometimes, even though you apply Kirchhoff's rules to two different parts of the circuit, you're really learning the exact same thing. Okay? It's a little bit obvious here in this simple circuit, but in more complicated circuits, you might apply it in two places, and you're actually not learning anything new. You can end up with sort of overdetermined circuits. So we may show you, or overdetermined equations. We may show you some later. If you're sort of messing around with all your algebra and end up with 0 equals 0, that means you over-applied these rules. But we'll get more into it as we keep going. And now we have Kirchhoff's second rule, the loop rule. mathematically, it's also a sum. It's the sum, if we go around a loop, that all of the potential differences on the different elements in the circuit will equal 0. So the potential difference, in words, potential difference around a loop is 0. So let's draw a circuit and apply it to see how we use this. So we're going to draw just the simplest circuit, our battery with an EMF up here, down to a resistor, and back around. There it is. So step 1 is to pick a current direction. Just like we did with the junction rule, let's just assume the current flows that way. And I don't need to put a number on it because there's only one current in this case. We only have one loop. Okay, pick current direction. And then 2, we need to pick a loop direction. They don't have to be the same direction. They won't always be when you get into more complicated circuits. But a loop direction means we're going to walk around this circuit, think about the potential, therefore we have to go in some direction. So I like to draw something like that, meaning we're going to go clockwise around the loop. You could go counterclockwise if you wanted to, but I just always go clockwise just to avoid confusion. And then you kind of need a starting place. You got to pick somewhere to start. Okay, so let's do it. So then what you do is then, step 3, let's say, is imagine a test charge. What that means is, imagine a test charge is sitting here, and let's think about all the potential differences it goes through, because it goes all the way around the loop. All right? So here we go. So I'm a test charge. Test charges are small and positive, so I'm a positive charge. I'm moving through this wire, and we know there's essentially no potential drop across the wire. We assume the wires are nice and conductive until it gets to here. And now we have a resistor. So it has a delta V. It has a potential drop. It has current flowing through it. We need to put in the delta V of this potential, of this test charge as it goes from here to here. We know this is the high potential. You have a potential drop across the resistor. So we know it goes down. And we know the potential, the delta V is IR. So now we just got to figure out what to put. Well, we're trying to figure out the potential across the resistor plus the potential across the battery. It's going to be equal to 0. So what do we put here? It's actually negative IR because it's a potential drop. Or if you think of it as a change, it's going from from a high value to a low value. So it's the low value minus the high value. So when you go through a circuit with the current, imagining your test charge, it's negative IR is the delta V, is the potential there. And then you keep going, and we get to the battery. Well, we know that the battery drives current flow, some electrochemical reaction in here, and we know this is the negative terminal, and this is the positive terminal. The longer line is always the positive terminal. So if you're a little test charge, you're here at a low potential, you go here, you go up to a higher potential, the final minus the initial is positive, so this is plus E, plus the EMF equals 0. All right. And then you solve that and see, well, this is the answer, and does it make sense? And in this case, it does. It just gave us Ohm's law. We know that the EMF from the battery equals IR. So that's how you do it, is you walk through the circuit. Now, you could do something weird. You don't really have to guess this current the right way. In more complicated circuits, you might guess the current the wrong way. So let's imagine what would have happened if we had said, oh, maybe the current will go that way. All right, we can do it real quick. If the current's going that way, and I'm a test charge walking this way, I'm going against the current. If the current's going that way, then this will be the high potential side, and this will be the low potential side of the resistor. So whenever you go against the current in your loop, then it's plus IR. Okay? And then you come up to this battery. Now, even though the current we've guessed one way or the other way, it doesn't matter. A battery always has a low potential here and high potential here. So for the battery, it's still plus the EMF. Okay? So the resistor cares about the current flow direction when you're getting the delta V, the battery does not. If you solve this, you get something, and you say, wait, this doesn't look right. That doesn't look like Ohm's law. the EMF is negative IR. But that is right because we guessed the current the wrong way. If you have the current set up this way, you better get a negative value for the current because we know it's really going to go that way. And sure enough, Kirchhoff's law is correct. Okay? So you actually can get any current direction, any loop direction, doesn't matter. You'll get the right answer. Just in most cases, if you can see which way the current goes, it's better to guess the right way. Now let's use both Kirchhoff rules for a multi-loop circuit. Okay, so we're going to draw one here that has, let's say, one battery here, and it comes up, resistor 1 there, and then it comes down and over, and say another battery, EMF 2 there, and another resistor, R2, and then it splits and comes down, and yet another resistor, R3. So this is one that you can't just look at and apply Ohm's law to instantly solve. It requires something a little more complicated. We need to apply our two rules. So first, let's think about the junction rules. So there's a couple of junctions here, one here and one here. So let's first define the currents. So I1, we'll say, is going to flow out of that first battery, go all the way till you get to here. That's the first junction. Then we need to split it up and say I2 goes there, and let's say I3 goes here. I'll draw it over here. And that defines all the currents. So here it's I1, here it's I2, 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 back to I1. And then here it's I3 all the way across here and back to I1. Okay? So the junction rule. You can pick either junction. We can pick this one and say I1 goes in and I2 and I3 go out, just like we had before. So I1 equals I2 plus I3. That's one equation. Now, what are we really doing here? Let's stop and think for a second. We're trying to find the currents in a problem like this. I'm doing it all symbolic, but what you would imagine is you were given a circuit with resistors and batteries in it. So say this is 12 volts and 10 volts and 10 ohms and 20 ohms and 50 ohms. What we're trying to solve for is the current in each branch. So we have three unknowns. Right here. There's already one equation. We know if we have three unknowns, we need three equations. So from the loop rule, we need two more equations. You might say, oh, we could get one more from the junction rule by looking at this junction, but that would be another case. That would be a case where you already have the same information. It wouldn't tell you anything different from this junction. So we have to go to the loop rule to get two more equations. All right, so for the loop rule, we've already defined the current directions. All we got to do is say, what loop are we going to do? There's actually three loops here. We could do this loop, the top half. We could do this loop, the bottom half, or we could do the outside. Right? So three possible loops. Let's start with the top half. Let's just go around it clockwise. It's always good to go clockwise. Let's start here. Okay, I'm a positive test charge. I'm going with the current. I encounter R1, so it's minus IR. So in this case, it's minus I1 R1, because I'm going with I1. So minus I1 R1 is 1 delta V. And I'm still going along, going along, going along, going along. And I come here. And now I go across this battery, but I go backwards across the battery. I go from the high potential to the low potential. So that's minus EMF 2. All right. And then I cross the resistor R2, and I'm going with the current I3. So that's minus I3 R2. And then in this loop, I go across the battery EMF 1, and I'm going from the low to the high, like you would expect. So it's plus E2 equals 0. So there's a loop. Now let's see. So that's two equations with our three unknowns. We just need one more equation. So let's do this bottom loop here. Okay, we're going to go clockwise around the loop. I'm going to start here. Here we go. Let's see, we're going this way, going this way. We're going to go across R2, and we're going against current 3. Yeah, so that means it's plus. right? We're going against, we're going from the low side to the high side. So that's I3R2. All right. And then we're going to go against, or we're going to go sort of with, from the low to the high of the battery, EMF2. So that's plus EMF2. And then we're going down across, here we go. And now we're going with current 2 across R3. So that's minus I2R3, minus I2R3. And then we're back where we started, so equals 0. So that should actually solve it. There's 3 equations, 3 unknowns. Here's one, I1, I2, I3. There's an unknown, 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 and unknown. All the other terms are known. You're going to be given a circuit with EMFs and resistances. And then it's just down to algebra, or if it's really complicated, linear algebra, to solve for the 3 currents. Generally, in sort of a freshman physics class, you'd be given circuits where it's doable by hand. That's usually what we hope for. It's not so simple that you can't mess it up. You can end up in your own little loop and never find the answer. So we're going to do an example for you with real numbers plugged in.